third part of the course, energy and energy transfer. We've already introduced the concept of energy. And what we're doing now is introducing work and heat as methods of energy transfer and then tie them together in the first law of thermodynamics. So what we'll focus on first of all is heat. But to put it into context, energy can be transferred in and out of thermodynamic system by work, heat, and mass flow. Work and heat we're going to define. Mass flow, as we mentioned before, is when the working fluid comes in the form, let's say, of steam into a turbine and brings energy with it. So the working fluid can bring energy into the system and cross the system boundary in the form of energy. So the other example then would be heat exchanger. Cold fluid comes in, there's a heat exchange from another warm fluid, and then we have the working fluid going out, taking energy with it in the form of a mass flow from the system. So in an open thermodynamic system like a heat exchanger or a turbine, energy can be brought in and out of that system by heat, work, and mass flow. But in a closed system, because the working fluid stays in the system and cannot cross that boundary, energy can only be transferred in and out by work and heat. And we're going to define those two terms now, and we're going to start with heat. So heat, or heat transfer as it can be described as, is energy in transit across a boundary due to a temperature difference or gradient. Simple analogy there would be a soda can. The working fluid is the soda, and the can itself represents the thermodynamic system and sets the boundary. And it's a closed system. So what happens is we've got the air at 25 degrees. The soda in this particular case is at 25 degrees. Although we have a boundary, we don't have a temperature difference. So energy in transit across a boundary due to a temperature difference or gradient is not the circumstances in this case. So there's no heat transfer. We look at the second example, and the soda is now at 15 degrees. So we have a boundary and we have a temperature difference. And in this case, it states that the energy is 8 joules per second. That's the heat transfer rate. And in the third example, the soda is now at 5 degrees. So there's a lower temperature difference. There's a greater temperature difference across that boundary. So there's more heat transfer. And in this case, it was measured at 16 joules per second. The SI unit for heat is the joule, named after James Prescott Joule, who identified the mechanical equivalent of heat that we mentioned in the first section. Heat always flows in the direction of decreasing temperature from hot to cold. And one other point to make about heat transfer, an adiabatic process, a process which we'll come across later on in the course, is a process during which there's no heat transfer. A couple of examples would be an isolated system like a thermos flask, for example, where heat can neither come in or out. And then a system and surroundings are in thermal equilibrium. So the first case here, where the soda is at 25 degrees and the air temperature is 25 degrees, they're at the same temperature, so there's no heat transfer. So that can be regarded as an adiabatic system in that case. A general equation to calculate the amount of heat needed to change the temperature from a substance from one temperature to another, for example, is this equation here. So heat transfer from one system to another is given by the following equation, and just a footnote there when no phase changes occurs. So what we have is the mass of the substance, the specific heat capacity, and the temperature difference. Though the different substances take different amounts of heat to different amounts of energy to heat up, and that's represented by the property, the specific heat capacity here. So we have the mass of the substance, the specific heat capacity, and the temperature difference. So the example there would be if we wanted to know how much energy it had taken, for example, to heat water in a container or a kettle up to a certain temperature, we can use this equation. So we'd have the mass of the water, we'd have the specific heat capacity for water, which is a constant, 4.186 kilojoules per kilogram Kelvin. And then we'd have the temperature difference, the temperature of the source and the temperature of the water. And we'll end up with a value in kilojoules. In rate form, we replace the mass by the mass flow rate, and we'll get kilojoules per second. And per unit mass, if we want to express it per unit mass in kilojoules per kilogram, we'll divide Q up here by M, or simply just drop the M value. Simple example, an object of weight 7 kilograms is heated from its initial temperature of 30 degrees to a final temperature of 60 degrees. Find the total heat obtained by the system. So how much energy do we need to raise this object from 30 degrees up to 60 degrees? The specific heat capacity of the material in question is 0.45 kilojoules per kilogram Kelvin. So we have the mass, we have the specific heat capacity, we have the temperature difference in Kelvin, and then it equals 94.5 kilojoules. Just note the units, the way they cancel, the kilograms are cancelling there, the Kelvin's cancelling here, and that's how we get kilojoules. Now, heat transfer can occur three particular ways: convection, conduction, and radiation. Convection is how the air is heated up and moved around, let's say, within the room from the radiators. Conduction is how we can lose energy from the building fabric of the home and through the walls, for example. And then radiation is how energy, heat is transferred from the sun by electromagnetic waves, and it can occur in a void or a vacuum, so it doesn't need a medium to take place. So more strict definitions for conduction, convection, and radiation are outlined here. Conduction is the transmission of heat through a substance without perceptible motion of the substance, and it involves microscopic collisions. So basically what that means is we've a higher temperature on this side of the wall, a lower temperature on this side of the wall. As the molecules and atoms heat up on the warm side, their kinetic energy increase, and then they start to collide and bounce off the colder atoms and molecules to the side of them. They increase in kinetic energy, and they in turn interact with the molecules to the side of them, and that's how conduction occurs through a solid surface. Convection is heat transfer due to bulk movement of a fluid, usually between a solid and a fluid. So if we have a warm surface here, what happens is the air molecules just above it heat up. They become less dense, more buoyant, and rise up into the air and are replaced by colder, more dense molecules. If we just leave the object sitting there in the air, that's called natural convection. If we force the air across it or the fluid across it by a pump or a fan, it's called forced convection. Radiation is the way the sun emits its radiation. It doesn't need a medium. It can happen in a void or a vacuum, and all surfaces that are above absolute zero emit radiant heat. So radiation here is defined as the transfer of energy by electromagnetic radiation with a defined range of wavelengths. All surfaces emit radiant heat. So conduction is governed by Fourier's law. It's the mechanism, another definition here, of heat transfer through a material by molecular diffusion due to a temperature gradient. A different way of expressing the same thing. If we assume that the heat flows through a solid in one direction only, with no variation in intensity of heat transfer, the flow is one-dimensional. So this is a simplification assumption that we make for this level of heat transfer. It's one direction and it's one-dimensional. It's moving in one direction and at the same intensity. And the rate of heat flow in the x direction due to conduction is written by Q dot x. It's expressed in watts and is defined by this equation here. So Q dot x is the rate of heat transfer in the x direction. K is the thermal conductivity coefficient in watts per meter Kelvin. A is the area through which heat transfer occurs, and T is the temperature. So Fourier's law states that the heat transfer rate through a material is proportional to the negative gradient of temperature and the area to which heat flows. Heat is conducted in the direction of decreasing temperature, and the temperature gradient becomes negative when the temperature decreases with increasing x. Therefore, a negative sign is added to make heat transfer in the positive x direction and a positive quantity. So basically, when we're getting our delta T here, the cooler temperature is put first, so you end up with a negative value here. So to make heat transfer positive, we put another negative into the equation. And the delta x here is the distance that we're dealing with down here. So we're dealing with the full distance through the wall. We can represent it as L, which is shown here as the length. So the thermal conductivity coefficient K in watts per meter Kelvin is a measure of a material's ability to transfer thermal energy by conduction. Materials with a higher K are better at conducting heat. So a few examples here of the thermal conductivity for different substances and materials. So a simple example, the roof of an electrically heated room is 3 meters long and 5 meters wide and 0.25 meters thick. It's made of a flat layer of concrete whose thermal conductivity is 0.8 watts per meter Kelvin. During winter, temperature of the inner and outer surfaces of the roof are measured to be 15 degrees and 4 degrees respectively. Calculate the rate of heat loss through the roof. So we have the area of the roof. So we're just looking at a two-dimensional image of it here. So if you can imagine the roof going this direction. So it's 3 meters by 5 meters, so it's 15 meters squared. We've got the conductivity coefficient here, 0.8. The temperature difference is 4 minus 15, so it's minus 11. And the thickness of the wall, the dx value is 0.25 meters. So we put them into our equation. So the double negative makes a positive, and we have 0.528 watts. And if you want to make it clear that you're dealing with conduction, put a subscript COND at the end. But what if we're dealing with conduction through a multi-layered wall? So walls often contain multi-layers of insulation with different values for the thermal conductivity for each material. So here we have a two-layered system. Rock wool, which would be regarded as a good insulator, so has a relatively low thermal conductivity value. Brick, which would be more of a conductor, so it has a slightly higher thermal conductivity value. So if we look at Fourier's law here, and we transpose it for the rock wool to get the delta T on its own, this is the expression that we get. If we consider the brick now and Fourier's law and transpose it to get the delta T on its own, this is what we get. So now instead of considering the temperature going through the temperature across the rock wool and then the temperature across the brick, we consider the temperature across the two layers. And to do that, we add up both of these terms together, and this is what we get. Now we multiply the A back into the brackets, and we transpose the equation to get delta T, to get the Q dot value on its own, and this is what we get. So now we have an equation helping us to calculate the heat transfer rate through a multi-layered system. And here it is. So what we have is we've got the temperature difference across the layers, and then it's the sum of the thicknesses of each layer divided by their area divided by the thermal conductivity values. So an example of how this is applied Here we have a three-layered system considering a plasterboard, raised block, brick. We're given the area as 25 meters squared, and we're given the individual thermal conductivity values and the thickness of each layer. So we have the temperature difference across the system, which is 4 minus 22. We've got the thickness of each layer divided by the area divided by the thermal conductivity. So for the first layer, we've plaster, and it's 0.012 meters divided by 25 meters divided by 0.1 watts per meter Kelvin. So we do that for each layer, add those values up, and divide the temperature across the whole system by what we get underneath. And the value in this case is 738.6 watts. So moving on to convection. Convection is heat transfer due to the bulk movement of a fluid, usually between a solid and a fluid. So free or natural convection is heat transfer due to the bulk movement of a fluid. Fluid motion usually caused by natural effects, such as the buoyancy effect. And forced convection, the fluid is forced to flow over the surface or in a tube by external means, such as a pump or a fan. Convection heat transfer processes satisfy Newton's law of cooling as follows. So you've got the heat transfer rate equals the heat transfer coefficient. So similar to the K value, just notice that the units are slightly different. It's watts per meter squared Kelvin in this case. You've got the area, which is perpendicular to the flow. So the heat transfer is going this way. It's the area here that we're dealing with. And then you've got the temperature difference. So the TS would be typically the surface that we're dealing with here. And then T infinity here is described as free stream temperature. In other words, the temperature of the fluid sufficiently far away from the surface not to be influenced by the cooling effect. So the ambient temperature of the room in most cases. If we're dealing with a situation where the heat transfers in the other direction from the fluid to the surface, we can switch our two temperatures around. The value of the heat transfer coefficient H depends on the type of flow, which affects heat transfer. So once again, if we force air across or some type of fluid across the surface, we'll increase the heat transfer coefficient. The geometry of the surface. So this is something we'll see in the lab. If we have a surface that has its surface area more in contact with the flow of the fluid, we can increase the heat transfer rate from the heat transfer coefficient from the surface. The type of fluid and its thermodynamic states, in other words, its pressures and temperatures, affected as well. So here you can see with oil significantly higher, steam, so on, significantly higher as well. So the thermodynamic properties, the geometry of the surface that we're dealing with, and the type of flow of the fluid in question can significantly change the H value. So hot air at 80 degrees is blown over a 2 meter by 4 meter flat surface at 30 degrees. If the convection coefficient H equals 55 watts per meter squared Kelvin, determine the heat transfer from the air to the plate in kilowatts. So in this situation, the air is warmer, so there's a heat transfer going towards the plate. So we take that into account in our equation. We've got our heat transfer value, which is 55 watts per meter squared Kelvin. We have the area, which is 8 meters squared, and we have the temperature difference, in this case 80 minus 30, and we end up with 22 kilowatts. Okay, so radiation, as I mentioned previously, it's the way the sun radiates its energy out towards the universe. It doesn't necessarily mean it need a medium. It can occur in a void or a vacuum. And it says here, thermal radiation involves the transfer of heat from one body to another at a lower temperature by electromagnetic waves passing through a separating medium. which can be a void or a vacuum. It's governed by Stefan Boltzmann's law, which states that for an ideal absorber, emitter, or black body, which I'll explain in a moment, the total radiant heat per unit surface area per unit time emitted from the surface is proportional to the fourth power of its absolute temperature. So, bit of a mouthful, but basically it's describing this equation here. To calculate the heat transfer from a perfect emitter or absorber, a material that absorbs or emits energy perfectly, or radiation perfectly, the equation is the Stefan Boltzmann's constant, which is a constant and will always be used, 5.67 by 10 to the power minus 8 watts per meter squared, Kelvin to the power of 4, by the surface temperature to the power of 4. And we end up with watts per meter squared. Now, to explain the concept of a black body, it's a conceptual idea. Basically, it's a perfect absorber and emitter of light and radiation. The analogy would be if you had a sphere, a hollow sphere, with a small pinhole in it, and if a beam of light came in and it bounced around forever and never found its way back, that's the concept of a black body. All surfaces deviate from being a black body, so there's no such thing in nature. They deviate to some extent, and that's taken into consideration by the emissivity represented by the epsilon symbol here. So we need to add that into our equation. So the ideal surface that emits radiation at the maximum rate is called a black body. The radiation emitted by all real surfaces is less, and it's given by this slightly adjusted equation. Now, to find the total power radiated by an object, we must multiply the radiant heat by the surface area. So now we're adding in the surface area in here to find the total power in joules per second. So just moving on to the black body thing again, all surfaces deviate from being a black body to some extent, and it's taken into consideration by the emissivity, which was represented by the epsilon symbol. So those values range between 0 and 1, 1 being a perfect black body. So you can see some values here in human skin, 0.95, and polished copper, 0.03. So an example, what is the rate of heat transfer by radiation from a person standing in a dark room at an ambient temperature of 22 degrees? The person has a normal skin temperature of 33 degrees and a surface area of 1.5 meters squared. The emissivity of skin is 0.97. So if a person standing in a room, temperature is 33 degrees, the room temperature is 22 degrees. We know the surface area and their emissivity value. So we have the Stefan Boltzmann's constant, we have the emissivity for skin, the area of the person, and the temperature difference. Plug those into the values and we get minus 99 watts is the amount of energy being emitted by the person under these circumstances. So the rate of heat flow per unit surface area is known as the heat flux. So we don't know the area, or we don't want to necessarily express it in terms of area. We can use the heat flux, which is represented by a small q with a dot and a double prime symbol. And it's basically the large q dot divided by area. So we get it not expressed in watts, we get it expressed now in watts per meter squared. And it's true for all modes of heat transfer. So one other property, heat transfer property that's important to cover is called thermal resistance. It's basically how much resistance a material is to heat flow. So if you think of the insulation in the wall of your home, you want it to have high thermal resistance to act as a barrier to heat flow. It can be expressed in a couple of ways. One, as the absolute thermal resistance here. So what we do is we get the temperature difference across the wall and divide it by the heat transfer rate. And the values are in Kelvin per watt. However, if we want to express it per unit area, we'd use the specific thermal resistance, or the R value, and it's the temperature difference across the heat flux. And it's watt meter squared Kelvin per watt. So let me read down through this, make sense of it. Thermal resistance is a heat transfer property and a measurement of how resistant the material is to heat flow. It is described as the relationship between the temperature difference across a substance or object and the rate of heat flow through it. So the absolute thermal resistance, or in SI units of Kelvin per watt, is the temperature difference across a structure when a unit of energy flows through it in unit time. It's a property of a particular component useful for systems or materials where both the area and the thickness are known, such as heat exchangers or electronic cooling systems. So it makes more sense to express it as absolute thermal resistance in these cases. However, when we're dealing with in the construction industry with the likes of insulation, we don't want to calculate it, take the whole area into consideration. We just need to express it per unit area. So that's where we use specific thermal resistance or specific thermal resistivity, which is R single prime, as the units of meter squared Kelvin per watt, and is the resistance to heat flow per unit area of the material. It represents how well a material for a given thickness resists heat transfer for each square meter of area, and is a material constant. It's used in the construction industry and is often referred to as the R value. So the R value is a measure of how well a layer of insulation, a window or complete wall or ceiling resists the flow of heat. The higher the R value, the greater the insulating effect. So the R value is useful because we don't want to be calculating large areas. So in this case, we just express it per unit area. And what we see here, that this relationship between the delta T and the heat transfer flux is linear, it's proportional, and it's defined by this R value. And what we can also see then is that for a particular material, let's say we had a wall that just consisted of concrete and had a specific R value for it, a specific thermal resistance. Now we can see, according to this equation, that what drives heat transfer in this case is the temperature difference. It's the potential that drives heat transfer. So for example, if your home leaks a lot of energy and you want to do something about it, but it's too expensive for you to go insulating and wrapping the house and doing the roof and changing the windows and the doors, one other measure you can do is to bring in heating controls and regulate the temperature of your house at maybe 18 or 19 degrees rather than letting it go up to 25 degrees, because you'll conserve energy in the home much better if the inside of the house is at a lower temperature, because there's less potential pushing that energy through the wall. So the R value is useful when measuring, for example, trying to calculate heat transfer through a multi-layered system. So we done an example earlier on when we dealt with multiple layers in a wall and showed how we can calculate that by with an equation. But we can use the R values to simplify that equation slightly. But where it really comes into its own is when we're dealing with a multi-layered system that consists of both conduction and convection. The R value is very useful for that situation. So here we have hot fluid flowing one side, cold fluid flowing another side, and a multi-layered wall in between. So what we would normally do is we'd use the R value and calculate the R value for each layer of this system and use that to help us calculate the heat transfer rate. So for example, it could be a heat exchanger. If this was one layer, we've had hot fluid on one side, cold fluid on the other side, and a separating wall. And another example would be a boiler. You've got hot fluid inside the boiler. You've got the air on the outside of the boiler. You have a separating wall, which is the tank. And you might want to know the heat transfer through the whole system. So there's two things that we need to prove here, first of all. First of all, we can represent the R value in terms of the thermal conductivities values and K values and the H values. And we need to prove that we can do that. So that's what I'm going to do on this slide. So consider a wall between two fluids at different temperatures. Heat flows consecutively through three layers by a combination of convection and conduction. So here we have separating wall. You've got hot fluid going this way, cold fluid going this way, and there's a heat transfer through the three layers. So it could be, for example, as I mentioned previously, either a heat exchanger or a boiler, where this is air, this is water. So convection through the hot layer is expressed by Newton's law of cooling here. Conduction through the wall is governed by Fourier's law, and convection through the cold layer, once again, is governed by Newton's law of cooling. If we assume that the heat transfer rate is consistent through the three layers, this is one assumption that we make for this level of heat transfer, so that it doesn't start to accumulate at the interfaces. So Q dot through this layer equals Q dot through this layer equals Q dot through this layer. And we know that the R value equals the temperature difference across the heat flux. So we consider that for the convection, for the first layer. And the Q dot, the heat flux, is basically the Newton's law of cooling without the A value. And what the delta T is above and below the equation cancel. So we're left at 1 over H. So what we're saying there is the R value for convection can be expressed as 1 over the heat transfer coefficient. Similarly, for conduction, we've got the R value equals delta T over the heat flux, which we've shown already. And the heat flux can be expressed in terms of Fourier's law. So the delta T is above and below cancel, and we're left with L over K. So the R value for conduction can be expressed in terms of the thickness of the layer we're dealing with divided by the thermal conductivity coefficient. And once again, for the cold fluid layer, convection, the R value can be expressed as 1 over the heat transfer coefficient. So that's useful to know that we can calculate the R values in terms of the heat transfer coefficients and the thermal conductivity coefficients. But one other thing we can do is we can take the three R values across the three layers and add them together to get the R total. And then if we divide the temperature across the whole system by the R total, we will get the heat flux, the heat transfer rate per unit area. So this is similar to, let's say, Ohm's law on electronic circuits. So we have the resistance in three resistances in series in an electronic circuit. We can add them together and get the R total. And it's the same in thermal resistance for heat transfer. Now we have to prove this. So that's what we're going to do on the next slide. So we take the overall temperature across the three layers. It equals the temperature across one layer plus the temperature across the other layer plus the temperature across the third layer. Now, if we look at the heat transfer rate through the hot fluid, for example, it's governed by Newton's law of cooling. And if we transpose Newton's law of cooling to get delta T on their own, we get the heat transfer rate divided by the heat transfer coefficient and the area. So we can put that in here to represent this temperature. And we can do the same for the second layer and the third layer. And what we see is that 1 over H is the R value. L over K is the R value, and 1 over H is the R value, and Q dot divided by A is the heat flux. And it's the same for the middle layer or for the third layer. Now, if we assume that the heat flux through each layer is the same, that there's no change in heat transfer through the systems, we can take that out of the equation. And now we've got delta T equals the heat flux multiplied by the R total. So basically the R total equals the delta T divided by the heat flux in meters squared Kelvin per watts. And this rule applies when the same heat flows in series through the layers. Okay, so that what we have now is a simple equation. If we have a multi-layered system that consists of a number of layers, what we can do is we can represent the R value for each layer in terms of the heat transfer coefficients and the thermal conductivity coefficients. Then we can add up those values and get the R total and divide the temperature across the whole system by the R total, and we will get the heat flux, the heat transfer rate per unit area going through that whole system. So a few complicated slides there, but ultimately it's taking us down to a very simple equation that we can apply to these complicated circumstances. So we've an example here. Consider a 1 meter high and 1.6 meter wide glass window. So that's the dimensions here and here, for example. It has a thickness of 10 mil and a thermal conductivity of 0.78 watts per meter Kelvin. Determine the steady rate of heat transfer per unit surface area through the glass window. So that's the heat flux. The temperature of the inner surface is maintained at 21 degrees, while the temperature of the outside is -2 degrees. Take the heat transfer coefficients for the inner and outer surfaces of the window to be 10 watts per meter squared Kelvin and 40 watts per meter squared Kelvin. So we have 3 layers, and what we're going to do is we're going to calculate the R value for the 3 layers and divide the temperature across the whole system by the R total. So the R value for convection in the outer wall is 1 over 40. Convection on the inner wall is 1 over 10. And conduction through the glass is the thickness of the glass divided by the thermal conductivity, which is 0.78. So we work all them out, and that's the lower part of the equation. And we've got the temperature difference across the whole system divided by the R total. And ultimately we get 166.9 watts per meter squared for the heat flux. Another example, a mild steel tank of wall thickness 10 millimeters contains water at 90 degrees when the atmospheric temperature is 15 degrees. The thermal conductivity of mild steel is 50 watts per meter Kelvin, and the heat transfer coefficient for the inside and outside of the tank are 2800 and 11 watts per meter squared Kelvin respectively. Calculate the rate of heat loss per unit area of the tank and the temperature of the outside surface of the tank. So we want to know the heat transfer rate to the whole system, and then once we know that, we can calculate this temperature here on the outside of the tank, which will be over here somewhere. Water on the inside of the tank, air on the outside of the tank, separating wall. And we have the values that we need. So the convection through the wall, the R value is 1 over H, so that's 1 over 2800. Conduction through the inner wall, the R value can be calculated by the thickness of the tank by the K value. And the convection through the air is 1 over 11. So the R total can be calculated. It's 1 over 10.93 watts meter squared Kelvin per watt. And then with temperature difference across the whole tank divided by the R total gives us the heat flux, 820 watts per meter squared. Now, what we want to do is we want to calculate the temperature on the outside of the tank, represented by TSR here. So we've got the temperature of the room. We want to know the temperature of the tank. We've got the H value for the air, and we know the heat flux, which is the same through the 3 layers. So we put our values, we transpose the equation, get the TSR on its own, and then we put our values for the heat flux, for the H value in there as well, and the temperature of the room. And we find that the temperature on the outside of the tank is 89.5 degrees Celsius. Okay, so bringing this together, the building's energy rating of a building depends on the level of insulation and energy consumption. It covers energy use for space heating, water heating, lighting and ventilation. So if you want to sell your home, you need a building's energy rating value. It's a measure of how energy efficient your home is, taking into consideration heating, space heating, water heating, lighting and ventilation, and gives you this overall value, which will give you a BER value on this scale. And one thing that feeds into the building's energy rating is the U value, which is basically the R total, the reciprocal of the R total. And it's a measure of how energy moves through the building fabric of the home. And the building fabric is basically the floors, the walls, the ceilings, the windows, and gives you this overall U value, which will feed into calculating your BER. So that's the other value that we needed to introduce, thermal transmittance, and it's just the reciprocal of the R total. And you'll see that the units in this case are watts per meter squared Kelvin as opposed to meter squared Kelvin per watts, because it's just 1 over the R total. So to bring this together, I'm going to play a short video.
Our lambda values, R values, and U values. Thermal insulation is measured by its ability to restrict heat transfer through thermal conductivity and thermal resistance. These are known as lambda values and R values, respectively. The lambda value, measured in watts per meter Kelvin, shows how well a material can conduct heat. The lower the lambda value, the lower the heat loss, and in turn, the better the insulation. The R value measures how well a material resists heat transfer at a specific thickness. This is calculated by dividing the thickness in meters by the lambda value and is measured in meters squared Kelvin over watts. A good insulation will have a higher R value, indicating it is better at reducing heat loss. So, what about the U value? This is the sum of the thermal resistances of all the layers that make up a building element, including any adjustments for fixings or air gaps. In units of watts per meter squared Kelvin, the U value shows the ability of an element to transmit heat from a warm space to a cold space in a building, and vice versa. It's also the figure you need to work to when meeting building regulations or standards. Essentially, the lower the U value, the better insulated the building element.
So that the lambda value that they mentioned there is basically the thermal conductivity value, K. And so that's a real world application of the theory that we've covered in this section. The next section for part 3 is we're going to be covering work, and then we'll bring it all together and finish this particular part of the module. Thanks.